It is related rates day 3. So if you are watching this video, please know that this is for someone who has gone through 2 days of related rates and has the knowledge, skills, attitudes, and perseverance to handle a 3rd day. I'll take you through a couple of these day 3 problems and why they are day 3. Let's start with this first one called the inverted conical tank problem. The radius of a conical tank is 1.9 meters and the height of the tank is 3.4 meters. Water is flowing into the tank at a constant rate. At the instant the depth of the water is 0.3 meters, answer the following. So these styles of problems with these boxes and the check marks, they came from a website that just kind of generated different numbers, and so you would practice doing these related rates problems and then put in the response and then check your answer. So we just froze these and have now what is our kind of our homework sheet with this converted or inverted tank problem with these numbers. First comes the D part, the diagram. Let's draw this inverted tank. It's going to be pretty basic for me. I'm just going to think of it as just like an upside down cone. And there's a water level. Let's put it right here. And we'll just add some value there to show that there's substance in there. And of the things that aren't changing, the radius is 1.9 meters. And the entire height of the cone, or the tank, is 3.4 meters. And I'm going to call that right now the before, because I know that at a certain instant the water is going to change because we're filling up this tank at a constant rate, and so there's going to be a time that is at a certain instant, what are the rates going to be? That's how related rates go. Let's go with the R for rates. That's the acronym DREADS. And so there are going to be rates that we know and rates that we need. And this first problem here, it says, at what rate is the depth of the water changing? We're going to need dH dt. And it's going to be at that specific place when the depth is 0.3 meters. So I'm just going to write a line and say h equals 0.3 meters because that's going to be at that specific time. We want at what rate is the depth of the water changing. We already know that the tank is being filled at 28.3 cubic meters a minute. That's dV dt. 28.3 cubic meters a minute. And so that's the R part of rates. For the E, for the equation piece, we need a way to link the volume and radius. That's the volume formula. Volume is 1/3 pi r squared h. Now, at this point in time, I'm going to switch over to the old red piece because now is where the related rates piece goes to day 3. We're going to need, when we observe a certain point in time, when this conical tank has a certain amount of liquid in it, I'm going to go here to like after. And I'm going to give it no, I'm going to go up here. Never mind. I'm going to go up here. This is some side work. This is what you need for day 3 and related rates. When you're observing an effect of something and it has to do with this conical tank or amount of liquid that is kind of filling space, the space that is made by some vessel, you can use similar triangles. So watch this. The radius of that whole tank is 1.9 all the way across, and the radius of where that water is, I'm just going to call R. The height of the entire tank is 3.4, and then the height of that water we're just going to call H. So because there are two triangles going on that are similar in a, I think you'd call it SAS situation, you don't have to know that from geometry. Here's the small one, and then here is the larger one. You can say, by similar triangles, small is to large as small is to large. So R is to 1.9 as H is to 3.4. Or you could say R is to H as 1.9 is to 3.4. You could, any way you could structure that proportion, you will get R equals 1.9 over 3.4 H, or H equals the reciprocal of that. So we're going to keep that in mind because that's a ratio that shows that no matter how much water is in there, it is always going to be, the height is going to be 19/34ths of, or the radius is going to be 19/34ths of the height. That's a key piece. So now we go back to the equation that we had, back to related rates, and where V equals 1/3 pi R squared. I'm going to substitute that. So now I know that I'm going to have V equals 1/3 pi, and I'm just going to have 1.9 over 3.4 squared H. Oh, sorry, 1.9 over 3.4 H squared times H. I do that because now I have just one variable. That's going to be handy. All right, I don't have my calculator with me. I'm just going to clean it up a bit, and that is V equals, so we got a pi and a 3 and a 1.9 and a 3.4, square that. I'm going to take the H squared out and make it an H cubed. So as I put a little red rectangle around that, that's my volume, expressed in terms of H. Okay, in related rates, we go dreads, D-R-E-D. Once we have that equation that links, we take the derivative of both sides. Okay, and I hope you're okay with me. Let's see. No, I'll rewrite it. V equals pi over 3 times 1.9 over 3.4 squared H cubed. And I'm going to take the derivative on both sides with respect to time, d dt. That on the left side is dv dt, and on the right side, all this stuff here, that's a constant. That's just a number. So I can wait and just take the derivative of H cubed. So it's going to be pi over 3, 1.9 over 3.4 squared times 3h squared. 3h squared dh dt. I see some things that can cancel. The 3 will cancel. That will be helpful just to kind of eliminate any extraneous numbers. And that means dv dt equals pi times 1.9 over 3.4 squared h squared dh dt. I'm going to put a little, just a brief box around that because that's the end of my derive station. And now DREDS is time for substitute. And that means wherever I have rates that I know or values that I know, I can put them in. We are looking for dH dt. So that here, this highlighted part, is going to be the one variable that or rate that we don't know. So 28.3 on the left equals pi. This is all going to go into a graphing calculator very soon. And then at that certain instant, our height is 0.3. So it's 0.3 squared, and that's dH dt. So at this point, you can put that all into a graphing calculator, and I think you're going to get, let's see, 28.3 over pi. And then that fraction, which is 1.9 over 3.4 squared, becomes the reciprocal, which is 3.4 over 1.9 squared on the other side, all divided by 0.3 squared. That should come out to be roughly 320.51. That's dH dt. Let's see, what are the units on that? H is the height, so that's going to be a linear unit. That's going to be meters per time, meters per minute. 320.51 meters per minute. And wow, where were we on that? That was what is the rate of the depth of the water changing. That's dH dt was around 320.51 meters per minute. You should always end with a sentence that encapsulates it. We've got more to do, so we're going to keep going with part B and find out what rate is the radius of the water surface changing. Much of this stuff will come up again, but I'm going to just make some space here for part B that we need now of the rates we know. Is dV dt, and that's 283 cubic meters per minute. But now what we need is how the radius changes. We need dr dt at that certain instant where h is 0.3. So the same things apply with that equation, which is volume is 1/3 pi r squared h, 1/3 pi r squared h. But now because we want to have how the radius changes with time, let's go back to that ratio from similar triangles and just turn it on its end. That means if we know r is 1.9 over 3.4 h, we can use that and just rearrange it a little so 3.4 r equals 1.9 h, and then h is going to be 3.4 over 1.9 r. We now have h expressed in terms of r. And so, where are we? Oh man, yeah, now we're going back and we're going to V equals 1/3 pi r squared. And now instead of substituting for r, I'm going to substitute for h. That's 3.4 over 1.9 r. That comes out to be 1/3 pi over times 3.4 over 1.9 r cubed. Now we get to the derived part, which means we take the derivative on both sides with respect to time, and that should yield dV dt equals, okay, 3. All this here, that's a constant. So I'll clean up later. It's 1/3 times pi times 3.4 over 1.9, and then the derivative of r cubed is 3r squared dr dt. I see a 3 that will cancel, and so I can clean that up and say dv dt equals 3.4 pi over 1.9 r squared dr dt. There is that certain instant where the height is 0.3, right? That's the certain instant. So now let's get to the substitute stage. And that means I know what dv dt is. That's 28.3, and that's on the right side 3.4 pi over 1.9. And I'm looking for dr dt, but r squared, when the height is 0.3, the radius is 1.9 over 3.4 times 0.3. I can find out that specific radius at that instant. I believe that becomes 0.168. That is at the certain instant where the depth of the water is 0.3. By similar triangles, you know that the radius is going to be 19/34 of it, right? Or 34/19 of it. R is always smaller than h, so it will be 19/34 of it, 0.168. All that comes out to be, let's see, we'll clean it up, 28.3. We can put this all into our graphing calculator. 28.3 divided by 3.4 pi. This is looking, I would love to clean this up a little bit more, 0.168. Whatever you get on the right side is dr dt. That should be around, I think I have 178.36 or 179, I think, maybe. I tried not to round at all except maybe here. I didn't store my value. It is something close. That is the rate of the radius of the water. 178.36 is dr dt. All right, good news. The surface area one, at what rate the surface area of the exposed water changing, that's pretty close. That means that at that certain instant where the radius is 1.9 and the water is here, and at that certain instant we know how the volume is changing, which is 28.3. We need now dA dt at that instant where the height is 0.3 meters. So that means this circle here, and I'm trying to make it a little more like 2D-ish, that is the surface area of the exposed water. It looks like a circle from the very top. There's water underneath it. We just want that surface area. And so the equation for that is just area is pi r squared. That's kind of nice. We've got d RE, we derive that equation on that's just above, that area problem. That's dA dt equals, and this would be one from like the first day of related rates. If you take the derivative, it's 2 pi r dr dt. All right, time to substitute. We know that dA dt, oh no, we're looking for dA dt. We have 2, we have pi, we have the radius at point 3. I think we found it. That's 1.9 over 3.4 times 0.3 from that previous problem. And then the dr dt, no, where are we? Oh yeah, dr dt was from the previous problem. That was around, I think I had 178.36. dA dt ends up being I have around 187. Two times pi times 1.9 times 0.3 times 178.36, all divided by 3.4, 187.85. Now this is surface area. It's a two-dimensional aspect. It's going to be square meters per minute. Whew! Congratulate yourself, everybody. Related rates are not easy. There's so much to keep in mind, so many things to refer back to. Congratulations.